let's say, development of techniques which we are trying to do, to go a little bit beyond the other conventional things which we do in strain tuning of properties. So what I'm going to do is I'm going back to the first iron-based superconductor, which is these 11-11 type systems, so lanthanum, oxygen, iron, arsenide. Actually, that was a system where iron-based superconductivity was discovered 10 years or more than 10 years ago. It's still the system which shows the highest TC. It's the only system which shows 60 Kelvin TC, which shows a TC which is substantially larger than that of magnesium diboride, the conventional superconductor. In some sense, let's say that this was the main motivation for doing so much efforts on these systems. Nevertheless, it's a system which is less explored, much less explored than all the other systems, and that was a simple reason, and that is that the materials properties are very much difficult. So it's very, very difficult to get crystals out of that. And I think we made at least some step in this direction, and that's let's say, the main thing which I will discuss in the beginning. So we have now a chance to get some crystals out of that. I will show you first phase diagram which you get out of single crystals. And then I will discuss in particular the nematic fluctuations. I will discuss the relationship between nematic fluctuations and the other orders which we have in this system, magnetism and superconductivity. And then I hope I have enough time to go a little bit further, so to go a little bit on strain-dependent things. So we are doing a lot in developing techniques under strain. So together with Clifford Higgs, we have an NMR cell, which now is operational up to pretty high strains. What I will show a little later on are elasto-Seebeck, so thermal power effect as a function of strain on these systems, on iron-based superconductors, and we have also measured the Nernst effect under strain. And currently, people are, again, in Berlin trying to get the ARPAs running under big strain. We'll see whether this works maybe a little bit later. Okay, a lot of people are involved in this. So as already told you, synthesis was a big thing, and that was done in SPICE team, but it was Rea Kappenberger, a PhD student. She was really made the breakthrough in single crystal growth for these 11-11 type systems. NMR Encurer, Hajo Graf is the leading person there. Then I will discuss a lot these, what people now call nematic susceptibility, so strain derivatives of resistivity. That's done in Christian Hess group, but it's Jiacheng Hong, who's the main player in this game. He's sitting here in the audience, and Federico Caglieres, who developed these thermal power and Nernst effect measurements under strain. And then we have also thermodynamics in there, and there's Rüdiger is here in the audience, Liran is in the audience. So where we studied mainly the phase diagram of these systems. So that's the starting point was, let's say, not a discovery. We just realized that when trying to optimize growing of polycrystalline materials, what we wanted to do, we saw that under some circumstances, indeed in such a solid state process, such large grains grow. Okay, and that was something which led us to the way to grow single crystals. It's an unusual growth process called solid state crystal growth. It's described in detail. If you want to have details, it's described in detail in this journal Crystal Growth article. It's a very strange thing. It's known also from the 60s of the last century. There are some rare exceptions where materials can be grown without using flux, and that's the main difference to all the other systems, to all the other compounds. It's also not this chemical vapor transport. So we really have a different way to grow crystals. And at the end of the day, if you're lucky and if you spend a lot of time and you optimize the process, you end up with such large, nicely faceted single crystals, which look very nice. They also look very nice when you look with the Lowell on there. So from crystallographic point, they're pretty nice. And there's also a chance to get that large, to get that even in the dimensions of what you need for neutron scattering. And that's what we are doing now. Now, let's have a look back to the systems. So we have a chance to get these single crystals now. These are a little bit the phase diagram. This is the old version of a phase diagram. We revisited this phase diagram because now, for two reasons. Now, of course, we have better control in the materials. And the second one is we have, in particular, found a way to determine this fluorine concentration, even with small concentrations. That's an NMR technique, which I will not describe in detail, only if you ask me. It's related to this Swiss cheese thing, which Ian Fischer mentioned this earlier. So it's just a peek here. So, but if you do that, you can really even take the old samples, can replot it, and they all fall on a single line. And at the end of the day, you end up with a phase diagram which looks like that. So these are now a few samples, new samples which we have. It's more or less very similar to the first version in the sense that we indeed have this very rapid suppression of magnetism. So magnetism disappears already at 3%, so at concentrations which are much, much smaller than this optimal doping region. So we really have an underdoped region which is non-magnetic, which looks very similar to cuprates if you want. We also can follow this nematic transition, but we lose it. So we have a big difference here in temperatures, but we lose this transition at some point. Everything becomes broad and disappears. But there is this line here, which I draw here, makes a lot of sense, and you will see it later on. So that's the phase diagram which we have, which we got from the polycrystalline samples, and you will see later on that we get a similar one for these first series of single crystals which we have. So now, I would like to emphasize or stress that these 1111 type superconductors are not very well explored, but they are really also very much different from the others. And I call them really very bad metals, if you want. So if you take this lanthanum, so this 1111 type compound, the parent compound, you measure the resistivity on the tiny crystal. That was the best, the smallest resistivity which I found at all. You still see something which does not look like a metal. So if you compare this to, let's say, lithium iron arsenide, which we also studied a couple of years ago, you see it's really very much different. There's even an enhancement here above the phase transitions telling you that there is enormous scattering going on. And then there is this nematic phase transition and then the magnetic phase transition. There's a drastic drop of the resistivity telling you whatever is the source of this high resistivity here, it's not extrinsic, because the mean free path becomes much, much larger when even opening partially a gap. You have a strong increase of the mobility, and it simply means that there is an intrinsic region for this bad metallic behavior, the very strong coupling to the other degrees of freedom. Okay, and this, of course, is not seen only by the single crystals, also seen in the early works. Only if you go to very high doping, you end up with resistivities which looks very similar to metal. You have a T-square behavior then at low temperatures. That's fine. It's also, you can also change it a little by chemical pressure. If you replace the lanthanum by samarium, which makes lattice a little bit smaller, bandwidth apparently becomes a little bit broader, so resistivity becomes a little bit smaller, but still these overall features remain more or less the same. So very bad metals. But still, these are the systems showing the highest TC, not the nice metals. Another example that these guys are really strange, this is what we have called, or what was called the poisoning effect, impurities. So if you start an optimal doped compound here, you add a ridiculously small amount of manganese, 0.2%. That's really nothing. You suppress superconductivity completely. And this, again, depends a little bit on the bandwidth. So if you go to samarium, the concentration is a little bit higher. You can fine-tune the thing by sizes. And again, this is not only superconductivity which you suppress here, it's also mobility again. It's again the fact that you drive the system immediately to something like an insulating, like a localized phase. And that's shown here. So that's already a sample where we made the system a little bit less sensitive to impurities of adding up in yttrium, so make lattice a little bit smaller. So you see, adding manganese, you go from a superconductor with a high TC to an insulator, and this is already a few percent. So this is really, I think, an extraordinary system. So now let's have a look on the magnetic and the nematic phase transitions in this system. And now I will first just flash what usually people do, and that's a lot of work has been done here in Karlsruhe, where people mentioned here around. So we have the lattice constant showing this orthorhombic strain here in barium 122 measured there. We have a softening of the lattice, which you can measure also by techniques which you already saw earlier by Anna's talk. We have the pioneering work from Fischer's group that we can measure the derivative of the resistivity, or the strain derivative of the resistivity, using these piezo things, showing this divergence, telling us that electronic degrees of freedom are crucial for this structural phase transition. We have magnetism involved, and that was discussed in the last talk in some details, also breaking this C4 symmetry, and of course orbitals play a role in order to understand that. So these are the typical experiments, and let's have a look on this for these lanthanum 1111 type systems. Most of them look very similar to 122. So this is a structural phase transition, the orthorhombic transition here, then tetragonal phase, measured by the capacitance teletometry. You also measure the lattice softening, again, very similar. So the structural phase transition is really very similar to that, what we know from the other systems. Also, the elastoresistivity shows a very typical behavior. We see the divergence here, telling us, again, this component of the electronic instability which is driving the system. You can fit this system by these Curie-Weiss laws. You get a Curie-Weiss temperature which is slightly smaller than the actual transition temperature, but this is all more or less standard. The NMR is already a little bit different than that what you find in the barium 122. You also plotted here is the relaxation rate as a function of temperature. At high temperature, there's hardly any temperature dependence. But then you have the structural phase transition, which you can directly detect in NMR. So there's a local probe for the structural phase transition. You see these two domains where the field orientation is parallel or perpendicular to the domains. You see the splitting, and then at temperatures 15 Kelvin below, you lose your signal, and that means you have a magnetic order. So in this intermediate temperature range between the magnetic phase transition and the actual Néel order, there's a huge increase of this relaxation rate. So that simply means this magnetic system becomes very soft, so correlation length increases incredibly. There is a pretty strong coupling between this nematic order here and the magnetism here. And in some sense, you can now put this system in between the iron selenium and the barium 122. In iron selenium, we have the nematic phase transition, and there is only a small change in the relaxation rate setting in at lower temperatures, and no magnetic order at all down to lowest temperatures. Here we have in barium 122, there's in the parent compound even simultaneously these two transitions. They are very strongly coupled, and here it's in between. So we have a clear splitting of the transitions, but there is really a substantial coupling between spins and nematic ordering in this system. Now, crystals. So the first series of samples which we have grown are cobalt-doped lanthanum oxygen, so lanthanum 1111 type systems. And it was clear from the beginning that these are lousy superconductors for a simple reason. And I've shown you these manganese doping effects. So what we are doing here, we add impurities. So cobalt is not only charges, it's also impurities. So that were lousy superconductors, but the reason to doing that is that it was the easiest way to control, to learn about single crystal growth. And what you can see here, we can go up to about 7 or 8% of doping. And the measured cobalt concentration, which you measure from EDX, correspond more or less to the nominal one. So this works. There is no work in progress. We want to do fluorine doping, samarium, cerium, and so on. That's all coming in the future. But this is the first series. The phase diagram then, which we studied, is again from thermal expansion coefficients. That's again the lattice constant, so the parent compound, 2.5%, 3%. There's shift of the phase transitions. You see also two phase transitions, structural one, magnetic one here. That's what we learned in the last talk by Anna. But what you also see is a substantial broadening here already, in particular of the structural phase transition going on if you start to dope these systems. You can also see that simply from the magnetic susceptibility. For the parent compound, you have these two phase transitions. If you add 1%, 2%, 3%, you still see the magnetic one remains sharp for something which is really funny, a reason which I do not really understand, whereas the larger anomaly due to structural, the nematic one disappears. This becomes very broad. So this we have then also additional measurements like NMR, where you can try to measure at least the structural phase transition by the line width. And you can measure, of course, the magnetic transition from 1/T1T. And altogether, you end up with this phase diagram. So again, the magnetism disappears. We can follow the magnetic order down to about 20 Kelvin. Then the splitting here to the structural one is pretty large, 60, 70 Kelvin. These phase transitions here are already very broad, and we lose the phase transitions if you go to higher temperatures. We simply do not see any signatures anymore of the thermodynamic phase transition. This, of course, is now very similar to this one, what we get from the powder sample. So it's more or less the same thing. So you lose You can follow the magnetic transition, sharp transitions down to low temperatures now. That's new in some sense for the new samples. We have this big splitting, and then we have this large underdoped region here where, okay, some nematic instability is still there, but we do not have a real phase transition. Let's have a look on the nematic, on this nematic susceptibility, so on the strain derivative of the resistivity. So if you go to 1%, 2.5%, you still see this Curie-Weiss behavior. If you do this analysis, you see that this characteristic temperature becomes smaller. So it was 140 in the parent compound, 120, below 100 here, 2.5%. So it's systematically decreasing. You can still, even in optimal doping, you still see this nematic susceptibility, still see this divergence here. Now, if you try to fit it, and the quality of the fit, of course, becomes a little bit worse, let me say that. But if you try to do that, you end up with a characteristic temperature here close to 0. And then if you go to overdope compounds, still see something like this strain derivative of resistivity, and now it becomes even negative. So you have a sign change of this Curie-Weiss temperature. And if you plot it, it looks like that. These are the whole set of series, the whole set of data which we have. So these are the Curie-Weiss temperatures which we get from the fits. So here it's close to the structural phase transitions, and we lose the phase transition somehow, but we can still see this characteristic temperature, and it hits 0 just at the concentration where we have optimal phase, where we have optimal superconductivity. It's just this additional line which I have indicated in the beginning. So that's fitting, but we can also simply plot these strain derivatives of the resistivity. So what we plot here is just the raw data, this d, r, d, and d eta. And what you then see just by naked eyes, there are somewhat two interesting compositions. One here at smaller dopings, and this is exactly where magnetism disappears. And the second one at higher doping, where we have superconducting dome. In some sense, we see both. And that's, of course, okay, just looking at the data tells us there is a coupling between these nematic fluctuations here and superconductivity. And as well, there is a coupling between spin fluctuations and nematic susceptibility. And the new thing, the new message which you get here is you can really separate that just from the materials. That's a new thing that you can do here in the materials. If you do the same experiment in the barium 1 to 2, which we also did, same plotting, same person measuring, it looks like that. That's what the usual thing is, and there these two transitions come together at the same thing. So that's really the difference here. And okay, and that's just this phase. This is this interesting underdoped region which we now have here, where we have these nematic fluctuations, where superconductivity comes up just there where we have enhanced nematic fluctuations. But we also know that there are nematic fluctuations strongly coupled to spins. So you also would expect very funny magnetic behavior in this region. This we did not study on the single crystals yet, but if you just look at the relaxation rate in the magnetic, in the NMR, so in the parent compound, magnetic order, huge peaks in 1/T1T, and these are now the samples, just these underdoped compounds. And in all these underdoped compounds, we have this very funny, very unusual behavior where some kind of freezing, very slow spin fluctuations, but not ending up to glass, not ending to a magnetic order. And I think that's something which is connected to these nematic fluctuations, which drives the spin systems, makes the system very, very unusual in any respect. And I saw something like that earlier when I did stripy cuprates back 20 years ago. There we also had this freezing of magnetic moments where we have the coupled not nematic, stripe order and a charge and spin stripe order. So very funny, very interesting underdoped region where we are far away from a conventional metal. And again, these are the systems showing the highest DC, not the nice metals.
What is the NMR you're using here?
Arsenic. It's always arsenic. Okay, so we can do some fitting on that. I'll skip that. So that's the situation. So how much time do I have? So.
10 minutes actually.
What? 3?
10 minutes.
10? Okay, that's fine. So then let's have a look on things which we are doing. So we use, just for historical reasons, due to the groundbreaking work of Fischer, we use resistivity to measure the nematic susceptibilities. But you could do a lot of other things to do that. Try to get some insight into the coupling between strain and electronic properties. And I will show you something. So, okay, together with Clifford Hicks, we have also developed these strain cells for doing NMR up to high strain. So now, meanwhile, sample is a limiting factor, sample breaks, and that's a limiting factor for the strain. You can measure electrical field gradients now, the local charge distribution at the arsenic nucleus, which you can measure at a satellite as a function, and you can do that as a function of strain, and you can plot that, and you can immediately see that it again follows these elastoresistivity measurements. Now, but that's of course a completely different probe. It's a probe which does not depend on scattering, which does not depend on details of the Fermi surface. You really measure the local charge distribution, and I think that really tells us that some orbital degrees of freedom play a role here. So, but you see the same curve, and I should also mention that Nick Currow, which is a colleague of us, a friend of us, also did some similar things and published that a couple of years ago. Okay, that's possible. That's one thing. But we can also try to use other transport properties. So other transport properties means resistivity measures scattering and measures density of states or number of charge carriers. But we can also use other transport properties like, for example, thermal power. So what we do there from experiment, we again take this usual technique. We have a piezo stack. Now we have a sample here glued on that. We have a heater, so we apply a thermal gradient on top of the, let's say, strain. And then we measure via the thermocouple this thermal gradient, and we measure the Seebeck effect, and we measure the Nernst effect. Nernst effect means the transverse effect, also famous from the cuprates. Nernst effect, there you have an additional magnetic field perpendicular to the sample, and you measure then the perpendicular voltages. Okay, so in principle, and Seebeck effect is known to be very sensitive on details of the Fermi surface. Nernst effect is even a little bit more complicated. So this is how the measurements look like. So you apply, you switch on a heater, and then you measure the thermal power. You switch on you change with the piezo, apply a strain. Strains are pretty small in this case. You see here the numbers. You still see a change of the thermal power here. It goes up, goes down again. Even there's funny situations that the thermal power itself changes sign, and the effect of the strain does not. So on top of that, and the same you can do with the Nernst signal, and that's also something what you also learned, that Nernst signal usually is zero in simple metals. Here in these systems, it's never zero. It's always pretty large. It's also interesting, and you can still resolve clearly the effect of strain on top of the usual Nernst signal, and then you plot it as a function of strain, negative and positive field, and you arrive at the Nernst signal. So let's have a look on the data. So this is now the Seebeck effect, first without strain as a function of temperature for these 1111 type compounds. For x equal to 0, it's close to 0. It even changes sign, as you have seen in the raw data a minute ago. And this is, telling you a number of holes and number of electrons are more or less of the same size, and you have some delicate balance between both. And then you have this phase transition, and there's a strong thing. If you go to the dope compounds, everything becomes negative, so you add electrons. Okay, that's fine. This we roughly, qualitatively understand. Typically, people discuss this Nernst effect in terms of Mott formula, so you measure the energy derivative of the conductivity close to the Fermi level. Now, the strain effect looks like that for these two compounds. So again, you see this strong increase. Now, what I plot here is the change of the thermal power as a function of strain close to the phase transition. You see this, again, this divergence. You can fit it in the same way. You can do it for the dope compounds as well. It follows also this temperature dependency. T star, which you get there, is also is of similar size than the Curie-Weiss temperatures, which I showed you from resistivity early on. So then, one referee told us you have to look you cannot take the absolute value, you have to take the relative value. But this is of course very funny here because it becomes 0 here at some points. So, or in other words, the Nernst effect here, charge carriers, so holes and electrons contribute somehow equally, leading to this thing which is close to 0, whereas these strain derivatives always has the same sign, it's always going in one direction. Again, telling us that when we discuss this in a multi-band system, this is band selective. Only one part of the story reacts in this thermal power. The next one, and you can also do that for barium 1 to 2, and it looks very similar.
So what is delta S again? What is being subtracted?
This delta is just a change as a function of strain. There's nothing subtracted. These are raw data. That's just a change. You have a 0 temperature without strain, and then you change it with strain.
There's no directionality involved like you would have in the elastic-resistivity. It's just, so which direction is the current?
That's exactly the same as in the elastic-resistivity.
Okay, so it's the difference between?
The difference between unstrained and strained sample in this direction,
okay.
Divided by the strain.
It's not the difference between this direction minus that direction.
No. That's no. In this case we did not subtract. We just measured that in one direction. Yeah. Okay, that's okay. This is correct. So it's just.
So you stated correctly what you did. I was just confused that
they
have the same symmetry.
Exactly.
No,
as the
yeah.
That would be a difference.
Maybe if you have to subtract the other thing, but it's measured in exactly the same way. No, you measure, you change the sample in one direction, measure the change of resistivity, measure the elastic effect. So the Nernst effect, that's even more strange, or that's really strange. First of all, so these again, okay, usually Nernst effect should be 0. Okay, it's not 0, okay, fine. Then this is the parent compound again of the 1111 type compounds. You have a huge anomaly, very strange anomaly, very strange behavior at low temperatures in this nematic phase. There's a very strong change already at the nematic phase transition here. Tiny or smaller or different anomaly at nil temperature, if at all. And then we have the dope compounds. Then in the high temperature phase, behavior is not so much different, but then in the ordered phase is completely different. Okay, but in standard picture, you would argue what you measure here is something like the energy derivative of the whole mobility. Okay, maybe we can discuss that later on. So often, so in simple metals, it's really 0. You cannot measure it at all. Often it scales somehow with the whole mobility divided by the Fermi energy. So if the Fermi energy becomes small, if there are some additional things going on there, it can become large. So now, the strain effect looks like that. Again, above, we clearly see this change as a function of strain. Again, as I mentioned, if you apply strain, measure the Nernst effect, and divide the changes by the strain. You can again, that's not a surprise anymore. You can again extract these stars. Okay, whatever you do, this temperature dependence is very similar. However, what you already see here, that the behavior at low temperatures is very much different. And what you also see is the numbers are very much different. And that was also the case in the thermal power. So the numbers change, and they change in a different way than they do in the resistivity. If you take the resistivity as an whatever nematic susceptibility, and you would do it the same here, then the concentration dependence would be different. And that's even more if you go to the Nernst effect. In the case of the Nernst effect, we also plotted it in this way, that we divided the Nernst effect by the number, and then again, then this picture becomes a little bit more clear. So again, you have this increase here, this usual nematic susceptibilities, if you want to call it here, and then there's a decrease at low temperatures. But these differences in I have to look where to look here. The differences in the absolute values is pretty large. And okay, since I have still some time, I will show you a little bit more on that, because in the Nernst effect, I think one more minute. Nernst effect is, these are the Nernst data for the whole series of samples. And here you really see something additional going on at x equal to 0. And if you do the same plot for the barium 1 to 2 compound, it's basically the same. And that's now, for me, it was a real surprise. So these completely different materials, 2-dimensional, more 3-dimensional, dirty, clean, bad metal, much better metal, nevertheless, you have more or less the same behavior here of these Nernst effect. There seems to be something which is really protected with respect to defects, with respect to dimensionality, with respect to slightly different band structure. However, if you add a little bit of dopants, 1% or 2%, it disappears, and then in both systems. There's something peculiar going on in this normal phase. And this looks like background here, but it's not. Also, this is a pretty large Nernst effect. If you plot it in this way in a logarithmic scale, you see, again, for both systems, very similar temperature dependence, 1 over Nernst divided by T, and linear in this logarithmic scale, very similar thing. Even details are very similar. So if you 2.5% cobalt doping, you have something like this going down here, 2.5% rhodium or cobalt doping here, it looks like that. For some reason, this Nernst effect in these two systems is very, very similar, though these are really nearly no metals, and these are very nice metals. It's very, very, very strange behavior. And then, if you have no explanation for this SIMS, what you can do is simply make a color fold plot, and it looks like that. This is the 1111 type compounds, and we know this now, what this is. So it seems that the Nernst effect immediately measured these nematic susceptibilities for some reason which we do not understand. And if you do it for 1 to 2, it looks like that, and that's very similar to that what you get from elastoresistivity directly. And here's no strain involved. That's just Nernst effect. Okay, that's it. So what I tried to show you a little bit is that we have some progress now in the samples for the 1111 type compounds. For the first time, we have these pretty large crystals now, which allow now more experiments. We can do much more on these systems. I showed you the first phase diagram, which we get for these cobalt dope compounds, where the main new feature is that we really have the well-separated magnetic and, let's say, magnetic critical point and superconducting, optimum superconductivity. So we have an underdoped non-magnetic phase where we have a lot of nematic fluctuations. We have evidence that these nematic fluctuations couple to both the magnetism and the superconductivity. And then we have I've shown the first data on Nernst effect, Seebeck effect, showing that all transport properties react on strain in these systems, and that maybe that the Nernst effect is really special because it could be a probe for the nematicity even without straining. So thank you very much for your attention.